Start recording. Okay, nice. Okay, let's continue this module. Okay, there we go. Okay, so we finished prismagnetism. So let's jump into the antiferromagnetism. So remember that all this prismagnetism is just part of a ferromagnetic materials, right? So we actually were covering ferromagnetic materials. Now we can have the opposite behavior materials, which are the antiferromagnetics. They exhibit, such as ferromagnetic materials, they exhibit a spontaneous alignment of moments of the magnetic moments, as long as they are below the created temperature, right? However, here is the difference with the ferromagnetic materials, is that the neighboring atoms in antiferromagnetic materials are aligned in an anti-parallel fashion. So basically, they're like canceling each other. And that is why the antiferromagnetic materials have no net magnetic moment. And antiferromagnetics, if I go above the Nil temperature, the critical temperature, they start obeying a linear law that is inversely proportional to, how do we call chi? What is chi? What was chi, guys? It's the susceptibility, okay? So these materials, once they're above the Nil temperature, they become paramagnetic and therefore obey a linear relationship or inverse relationship between the temperature and the inverse of the susceptibility. And you can see that here. So this is below the Nil temperature, but once they reach the Nil temperature, they follow this linear relationship between temperature and the inverse of susceptibility. And this is known as the Fourier-Weiss law, the linear relationship, okay, above the Nil temperature. So as we see, below the Nil temperature, the inverse susceptibility rises with decreasing temperature, right? We can see some data, okay, for the Nil temperature of different antiferromagnetic materials. You have very low temperatures like 67 Kelvin. You can have a bit higher like chromium or cobalt oxide, which are above the which are above room temperature, right? Because this is in Kelvin. Okay. The Fourier-Weiss law, yeah, it's modified for antiferromagnetic materials. It actually has this, I would say, this adjustment term that is theta, and you also see the values of theta here in this table. The Fourier-Weiss law, remember we saw that law. It applies for very few materials, okay? And in this case, it can be applied to antiferromagnetic materials above the nil temperature, but with this correction term. Okay? It's this correction term of negative theta, right? Just to make it a positive value overall. This was completely empirical, right? So there's not really an explanation for this yet. This was entirely empirical. Most antiferromagnetic materials are ionic compounds, and obviously they are insulators or at most semiconductors. And practical applications of these magnetic materials, really, there is not really one big application, important application in terms of engineering. So they just behave the opposite way of ferromagnetics, but there's not really a practical application for these materials or for materials that exhibit this property. Let's go with one of the important and very practical types of magnetism that is widely used in different applications, and that is ferrimagnetism. And I want to make sure you guys are not confused with ferro and ferrimagnetism. They're different, okay? Ferromagnetic materials are, among all magnetic materials, I would say they are the most technically important materials. So they are the ones that are mostly used in several applications. They also exhibit a spontaneous magnetic moment. They also have a hysteresis loop below the created temperature. So they are similar to ferromagnetics. The thing is that all the magnetic moments do not align in the same direction. And you might remember this from your ceramics course. So yes, you will have electron spins that will spontaneously align in parallel. But it's not that all electron spins align in the same direction. There will be some that will align in the opposite direction. So there will be a partial cancellation, but not a net cancellation of the magnetic moment. And that's why actually ferromagnetic are mostly oxides or obviously ceramics, and they are usually very poor electrical conductors. And in general, you really need that. You actually need a very large resistivity, so a very poor conductivity, especially for high frequency applications. And we'll see some of the applications in a bit, so bear with me. Neil proposed, or Neil tried to explain what's happening and how is this that this spontaneous magnetization in ferromagnetics is happening. And he said, okay, actually there should be in the microstructure two sublattices that should be or that should contain spins that are aligned parallel to each other. The difference is that these sublattices do not contain the same number of magnetic ions. That's why I said in ferromagnetic materials, there are some magnetic moments that remain uncancelled. So there is a cancellation, but it is only a partial cancellation, not a net cancellation, like it happens in antiferromagnetics, for example. So there is a net magnetic moment. And in terms of temperature dependence, ferromagnetics behave the same way to ferromagnetics. So that is, the saturation magnetization decreases with increasing temperature. So you can have here, it decreases with increasing temperature until it vanishes at what? At the Curie temperatures. Once I'm above the Curie temperature, ferromagnetics become paramagnetics. And there will be a nonlinear 1 over chi relationship, or relationship between temperature and the inverse of the susceptibility. So you could easily say, or you could argue, that ferromagnetics are imperfect antiferromagnetics, because they do have the same idea, right, of magnetic moments aligning in different, in opposite directions and canceling. The thing is that they do not have the same amount of magnetic moments, and therefore there is no net cancellation. Okay, any questions so far, guys? Okay, so far we basically tried to briefly explain the difference between paramagnetics, diamagnetics, ferromagnetics, antiferromagnetics, and ferromagnetics. But obviously from, let's say, more of a traditional point of view, let's go and deepen that that understanding, and let's start picking up on several quantum mechanics concepts, and try to relate them to these to the different types of magnetism, and obviously start dealing with some equations that arise from that. We definitely, I definitely don't want to explain every single theory for this, because that will take us a long time, and I'm sure that will confuse you a lot, and you don't really need to know the like the fundamentals of every single theory. So I'm going to start picking on the most relevant and probably important things you should know, and obviously just present the equations of that. So diamagnetism was explained from a quantum mechanics point of view. It was explained by Langevin, and he came up with this equation. So the idea is that he derived the susceptibility for diamagnetics as a relationship between the magnetization and the magnetic field strength, right? And so, well, he obviously then replaced these terms and then came up with this final equation. And you might be wondering, okay, so what do the terms in this equation mean, right? So what you know what it means. It's the electron charge, nothing to be surprised. This, first of all, this N naught density over W. So N naught, as you might imagine, is Avogadro's number. This is delta, is the density, right? And W is the atomic mass. So this term you have here, you can say it's actually the number of atoms per unit volume. This whole term here, it's the number of atoms per unit volume, right? Because you're relating the atomic mass, the density, and Avogadro's number. Okay. E is the electron charge, you know that. M is the mass. R is the average radius of electron orbits. What's mu naught? That's the permeability, right, of free space, and Z is the atomic number. Okay, so those are all the terms you have there. And actually, if you start putting numbers there, you will get susceptibilities between 10 to the -5 and 10 to the -7, which is actually quite in agreement with experimental values. So, and then we can start seeing, again, I'm not going to explain in detail the theory, but then you can start saying, you can start seeing why it's actually so important to use quantum mechanics, because if we try to model and try to get a value for the susceptibility in diamagnetics, you definitely wouldn't get a value close to experimental values. Whereas if you model this from a quantum mechanics point of view, and start using electron charge, mass of the electron, radius of the orbit of the electron, the atomic number, the density, the atomic mass. So if you start using terms from a atomic point of view, then you get values that are actually close to experimental values. And another interesting thing, you can see here there is no temperature term, and that's also quite in agreement with experimental values, because in diamagnetics we said actually susceptibility doesn't change with temperature. It changes, but very, very little, extremely small change. That's why, again, actually all the properties for diamagnetics, they're actually temperature independent. Okay, any question, guys? Okay. Now, Langevin also sort of adapted his theory, and he also derived, let's say, a theory for paramagnetism based on how electrons orbit, right? And he basically related that movement of electrons orbiting around the or around the nucleus. He related that to the behavior of paramagnetism, and actually works quite well. And he related this, or tried actually to support with this theory what Curie-Weiss, so the Curie-Weiss law, did, right? So we saw that paramagnetics do have or do change their behavior with temperature, right? And so we expect that a theory that is trying to explain the paramagnetic behavior should include a temperature term, right? So actually what Langevin did is he didn't treat a spin paramagnetism. And he came up, or he derived this equation, as long as we're not dealing with high field strengths. So if we're used, or we are in a condition where H is quite large, so the field strength is extremely large, then this equation doesn't work quite well. But if we are dealing with normal field strengths, then this equation works extremely well. And we can see here this does depend on temperature, right? And if you remember, there was an inverse relationship, right? Just remember the previous graphs. There's an inverse relationship between susceptibility and temperature for paramagnetics. And you can see here that. So you know the terms, KB is the Boltzmann Mu naught, remember, is the permeability to free space. What is mu m? It's called the magnetic moment, okay? Mu m is the magnetic moment, and n is just the number of magnetic moments. I guess that's the easy way of calling it, right? It's just a number that sort of tries to explain how many magnetic moments a material has. So this is actually the Curie and Weiss law, or Curie's law, as it's also known. And you can see, so that's why in some books you will find, because this is actually a constant for a material, right? You will find in some books that this is just grouped as a whole term, right? All this, and that term is denoted by C. You will find that in some books because it is a constant, so it's called the Curie constant. And you can see the relationship, or the inverse relationship, between temperature and susceptibility in paramagnetic materials. So if we actually replace values, we will find values that are small and positive, which again they are quite in agreement with experimental values for the susceptibility of in paramagnetic materials. Any questions, guys? Is everything clear? So just to remember, the Langevin theory really focuses and applies when paramagnetism is an important contribution. Remember, we saw that some materials can have a contribution to diamagnetism and can have a contribution to paramagnetism, but then one will be more prevalent than the other, right? And so paramagnetism derived from spins, it's not accounted by this theory. Why? Because this type of paramagnetism is only slightly temperature dependent. Here we're really looking at the electron orbit paramagnetism, the one that really changes or is affected by temperature. Okay. So let's continue with this theory. So just looking at that equation, we can definitely see that for a given temperature and for small values of the field strength, the magnetization is a linear function of H. If we're given a temperature and we have a small value of H, small value of the field strength, we can say that there will be a linear relationship between the magnetization and the field strength. Now, if we go to large field strengths, the magnetization, look, will eventually reach. So look, here, linear relationship, right? Linear relationship between magnetization and magnetic field strength. If we go to large field strengths, so this regime, then the magnetization will eventually reach a saturation value. You can see it's actually approaching, it's like an asymptote, it is approaching the saturation value. What does that mean? So it's basically saying that a limit is reached. And at that limit, what happens is that all magnetic moments are aligned to their maximum value. That is the meaning of reaching the saturation magnetization. So remember, this basically, or Langevin theory, is explaining what Curie and Weiss observe empirically, so observe experimentally, that the dependence on temperature of the inverse, or just the relationship between susceptibility and temperature, right, and how that inverse relationship occurs. Now, we can even go deeper and use more quantum theory and refine even further this theory. And Beryllium, remember the Beryllium zones? He actually did, or he actually used this already quantum mechanics theory and refine it with more quantum mechanics concepts. And so he took into account, and he said, well, not all values for the magnetic moments will be allowed, such as like the Beryllium zones, right? So not all, he said, well, shouldn't all values for the magnetic moments be allowed? He said, actually, the angular moments that we have orbiting, they should be quantized in an external magnetic field. And so he termed that as space quantization. So he basically said, okay, there should be only certain domains or certain magnetic domains that will be able to align according to the external magnetic field. And that's why he said, well, such as like in the Beryllium zones, in the energy bands, that there is an energy quantization. He said, well, here there should also be a space quantization, right? So he said only certain magnetic domains will align. And that leads to the Beryllium function, and that just what does is at the end is just you put an extra term here, okay? You just add here an extra term um, in that equation, and that is called the Beryllium function, and that just improves further, or allows you to get values even closer to experimental values, right? But again, I think that's taking the course too much in advance, and I don't want to do that. Okay. I think that should be the most important thing for at least paramagnetism. Any questions, guys? Okay. So let's compare between para and diamagnetism, right? We just talked about the two theories, both derived by Langevin. So let's see what the applications are, and obviously relate that to quantum mechanics. So remember that each electron state may be occupied by a maximum of two electrons, one with a spin up, the other with the spin down, right? Let's take that analogy to magnetism. So let's consider that you have a certain distribution of spins in one domain. And let's consider an electron band. So here are the electron bands, or the energy bands, right? There you go, energy bands or electron bands. Now divide that, let's divide it into two halves. One half will have a negative spin, this one, and the other will have a positive spin. Under normal conditions, these two halves will be occupied by the same number of electron spins. So if this has, I don't know, 10 electron spins, well, this should have 10 electron spins. Obviously, the left will be occupied by negative spins and the right by positive spins. Okay, let's just basically take that analogy of electron spins and use this. Well, that is under normal conditions. What happens if I apply an electric field? Okay. If I apply this external magnetic field, especially to a solid that has free electrons, well, those electrons that are unfavorably oriented spins, so in this case, look, my magnetic field it's oriented on the positive direction, right? So those electrons that are unfavorably oriented, some of those electrons will start to change their field direction. So look at that. Now I don't see the same number. You now see a difference, right? So now I have more electrons that are aligned with my magnetic field. And that is because some of these electrons that were unfavorably oriented just oriented the same way as the magnetic field. So they change their field direction. Well, that can happen only when those electrons, or with those electrons, that have an energy equal or higher than the Fermi energy. That can happen only in those electrons that have an energy equal or higher than the Fermi energy. So those affected electrons will assume an energy that is at least equal to the Fermi energy, because all the lower electron states of opposite spin directions are already occupied, right? So what I mean is, okay, so if my Fermi energy is here, right? And I want to jump to, or just change my spin, right? If I want to change my spin, let's say from here to here, actually, this might be easier to understand. I want to turn from here to here, right? So, okay, I do it. Okay, I realign myself, I reorient myself, that's fine. But if I'm gonna do that, I have to come here, right? I cannot come here because they are already occupied. These electron states are already occupied. So if I wanna come, I have to come here. Therefore, I need an energy that is at least the Fermi energy or higher, right? To be here. And that's what happens here, you see? So in theory, actually, right, this transfer of electrons from one half to the other will sort of cause two individual Fermi energies, right? Because that's what you're looking at here. It's like you will have one Fermi energy for this half, because remember, the Fermi energy is the maximum energy that the electron states that the electron can occupy. And then you'll have more electrons, you will have another Fermi energy there. But we know that is not possible, right? That cannot happen. And so what occurs is that these two band halves will shift relative to each other until we reach equilibrium. And obviously equilibrium means one single Fermi energy. So what happens? What happens from here to here? You can see it's just they shift, so they move so that both can be aligned. Yes, I still have more electrons here, obviously. Look at that. I have obviously more electrons, but now I have one single Fermi energy, right? So they just shift relative to each other in order to reach equilibrium. That means in order to reach a one single Fermi energy. Is it clear? Any questions? Okay. So this is really taking paramagnetism and diamagnetism to quantum mechanics. And this will actually allow us to understand why certain materials that should be paramagnetic are actually diamagnetic. And why is paramagnetic susceptibility relatively small for most metals? And why most metals do not obey the Courier-Weiss law? So these little concepts, okay, will actually allow us to understand why certain things that we expect in materials with respect to paramagnetism do not occur or occur in a different way. Okay? So that is okay, the first part of this. Let's continue. Now, we have this so we divided our electron band into two halves, right? One with a positive spin, the other with a negative, and we saw under the influence of a magnetic field what happens, right? Now remember that the electron distribution within a band is not uniform. Remember, I have a band, but the distribution of the electrons in that band is not really uniform. Remember, we have this parabolic distribution according to the energy states. So let's take back this concept that we haven't talked about in a while, I believe, is the population density. Remember, that is how the electrons are distributed in a band, right? This function, population density, is what determines that. And you might remember that when I'm close to the Fermi energy or around the Fermi energy, I actually have a very large population density, right? Therefore, if I have a small change in energy, that obviously is provided by that external magnetic field that I apply, this external magnetic field. Because I have so many electrons there, well, that small change in energy may actually cause a large number of electrons to switch to the opposite spin direction. And that's why this changed to this one. And that is why I have, you can see, just look at this, right? You have this space left here empty for the, let's say, negative spins. It's the same here. You have this space empty. And that is because obviously these electron states, the energy states, sorry, are only occupied by electrons that have a positive spin, by those electrons that reoriented themselves with the magnetic field. Okay. So this is actually, from this, we can actually find the susceptibility from this changing energy. Right? And this changing energy is represented as delta E. And obviously, the larger the magnetic field strength, the larger will be that changing energy, right? So if I put a stronger magnetic field, if I apply a stronger magnetic field, obviously this will be even higher, right? And that also affects the magnetic moment of the spinning electron. So if I apply a stronger or larger magnetic field, that will also cause a larger magnetic moment of those spinning electrons. So this is the equation that allows me to relate the magnetic field strength with that change in energy and the magnetic moment of the spinning electrons. You not remember, you already know what that means. Okay? Now, can I get the number of electrons that actually transfer from one domain to the, or from one half to the other? Yes. I can get the electrons that change from, let's say, a spin down to a spin up. And that also depends on, as you can see just from the graph, that depends on the density of states at the Fermi energy and the energy difference. So this delta n, so just this number of electrons, right, is proportional to the changing energy and the population density, or density of states at the Fermi energy. And that's equal to the magnetic, or that is proportional to the magnetic field strength, the magnetic moment, and the population density, or density of states at the Fermi energy. Any questions? Okay. So let's continue, and just, I guess this is more to have other equations that allow us to get at the end, the final or the end goal is to find a relationship for the susceptibility, right? So let's actually try to do that in magnetization variance. So just the relevant terms that describe the magnetic properties in a material, right? So we know that the magnetization in a solid is just given by the magnetic moment and the volume, right? If I have more electrons transfer, that will also affect the magnetization, right? So we can just adjust this equation to end up with something like this. We already saw all those terms there, so nothing to explain. Now I want to get at the end, as I said, an expression for susceptibility, right? So remember that susceptibility is just the ratio between magnetization and magnetic field strength, and you end up, just replace for that, and you end up with this equation. We can replace that magnetic moment of the spinning electron, so that mu ms, because that actually equals one Bohr magneton, and that is actually a constant. That, remember, I explained that constant in last class. So it's the same equation, just replaced with this, with the Bohr magneton, with mu b, right? Mu b is the Bohr magneton, and this is the equation for a spin paramagnetism, which differs, you can see here, low temperature. For electron orbit paramagnetism, where was it? Look, electron orbit paramagnetism, we have temperature. For spin paramagnetism, we do not have temperature. So if you want to calculate the susceptibility for metals, for example, which are or which strongly depend on spin paramagnetism rather than electron orbit paramagnetism, you can actually calculate with this equation, and it works perfectly well. It will give you values that are extremely close to experimental values. Any questions? So, what is this theory telling you? That only those electrons that are close to the Fermi energy are capable of realigning in the magnetic or with the magnetic field under that magnetic field. If you will try to calculate, as we were doing, just remember the first module, right? There was a huge difference between saying, okay, all electrons can jump from one energy state to the other, in readapting that and say, no, only those electrons close to the Fermi energy. Well, here's the same. If you will assume that all electrons contribute to the spin paramagnetism, then you will definitely get a value that is extremely wrong, 3-4 orders of magnitude larger than the one you can obtain experimentally, and that is because, again, not all electrons are capable of doing that, only those electrons close to the Fermi energy. Okay, let's continue with this. Remember that diamagnetism will be pretty much always present in all materials. And obviously, depending on the material, it will make a contribution that might be small or might be big. If we're talking about metals, actually, the diamagnetic susceptibility or diamagnetism will actually make an important contribution to the overall susceptibility that metals have. And it can actually be positive or negative depending on which predominates, either the paramagnetic behavior or the diamagnetic behavior. So let's consider the case of beryllium, right? It is a bivalent metal. If you look at the electronic configuration, you will find that it has a filled 2s shell in its atomic state. So not an ion or anything, just atomic state, it has a filled 2s shell. But if you make or put that material in a crystalline state, you will see a band overlapping. You can see here, there is an overlap between the 2s band and the 2p band, right? There's an overlap of bands. What happens, or what does that mean? Well, some of the electrons that are in the 2s band will spill over, so will move into the 2p band. And obviously, they will populate the top of the 2s band, which is equivalent to populating the bottom of the 2p band. So that's why you see this part is filled by electrons. So when this happens, right, the density of states at the Fermi energy, and obviously the paramagnetic susceptibility, is very small. And that's why, for example, in beryllium, diamagnetic susceptibility is the one that predominates, and it makes actually beryllium a diamagnetic material instead of a paramagnetic material. Now, let's also consider, for example, copper. Why is copper diamagnetic? Just kind of interesting. So remember Remember that in copper, and you might remember, if not, just go back to module 2 electrical properties and go and look at the band structure of copper, and you will see there that the Fermi energy is close to the band edge. So it's really, really close to the band edge. So where the band ends, you will see the Fermi energy is literally very, very close to that. So when that happens again, it's sort of the same here. The density of states near that Fermi energy will be small, and that's also why the paramagnetic susceptibility is small. So it kind of looks like this. You don't see a band overlap, but you will see like this too. So the Fermi energy very close. Look at the Fermi energy and look where the band starts or where the band begins. So look, it's just this space, this small. Let me show you with the pointer. It's just this small space here. So the same happens in copper. That is why you have a density of states small near the Fermi energy, and that is why you have a very small contribution of paramagnetic susceptibility, and that's why copper is diamagnetic. In addition, remember that the diamagnetic susceptibility is proportional to the square of an electron orbit radius. Remember the equation? There you go. Where is it? Here. Look, it's proportional to the square of that electron orbit radius. So, and also proportional to the number of electrons, right? So copper has 10 3D electrons. Yeah, just go and look at the electronic configuration, right? So that will obviously make the number of the total number of electrons approximately 10. And remember, S shells very small orbit radius, P shell a bit larger, D is fairly large, and F is even larger, right? So D is fairly large, so that makes R very big. Z is also big, and that's why the diamagnetic susceptibility is quite large because of these two contributions, because the radius of the D shells is relatively large or fairly large, and also Z is very large. So that will lead you to a large value of diamagnetic susceptibility, and again, that is also why copper is diamagnetic. So we have a diamagnetic contribution dominating over the paramagnetic contribution, and that also applies, sorry, for silver, for gold, and for all other elements that, if you look at the periodic table, follow copper. Now, what will happen, for example, with intrinsic semiconductors? Remember, intrinsic semiconductors have filled valence band, and their density of states at the top of the valence band is zero, right? Remember, it's very close to zero. Remember that density of state distribution for intrinsic semiconductors. Therefore, based on the equations, they will have no paramagnetic susceptibility, and therefore are diamagnetic, right? So, just in short, you can say, if I have a small density of states near the Fermi energy, well, that's obvious. I have no many electrons capable of realigning. Therefore, I have a small paramagnetic behavior, and therefore my material will be diamagnetic. Now, if you dope, let's say, intrinsic semiconductors, you will definitely have at least a small contribution of paramagnetism. Okay, let me finish with this, I guess, and then we'll go to the coffee break. I'll finish with this slide at least before going to the coffee break. So let's see now how the temperature, or what's the temperature dependence of the, obviously, of the susceptibility in metals, right? Either for the paramagnetic or the diamagnetic. Oh, this is just the equation that I showed you before. Anyways, okay. So for the paramagnetic susceptibility or the diamagnetic susceptibility in metals, we see that they do not really change with temperature, right? There's not really a dependence on temperature. And that is why you can safely argue that the susceptibility of diamagnetic metals and materials in general, but especially metals, it doesn't change with temperature. Whereas the susceptibility of paramagnetic metals doesn't obey the Fourier-Wise law. Actually, you can see the graph. The temperature dependence of the susceptibility for different paramagnetic metals, sorry, it can either decrease, it can either increase, or it can remain constant. So, for metals, there's not really a clear dependence on the susceptibility. In some materials, in some metals like vanadium, it decreases. In some metals like chromium, it increases. In other metals, it remains constant. So metals in general do not obey these laws of susceptibility depending on temperature, and that's why they also do not obey the Fourier-Wise law in like other paramagnetic materials do. There's only one exception: nickel. Nickel above the Fourier temperature, and some rare earth metals too. They do obey the Fourier-Wise law above the Fourier temperature. So once they become paramagnetic, right? But then other metals do not really obey it and do not also have this, or there's not a clear relationship between susceptibility and temperature. But in general, most metals actually, they definitely do not change their diamagnetic behavior with temperature. Okay. Any questions, guys? Is it clear?
Yeah, it's okay.
Okay. So time for coffee break. Georgina, you're pending, I think, to present.
Yes, yes.
Thanks. I forgot to, did I choose someone last week, guys, to present today or no? I forgot. I don't think I chose someone. So okay, go ahead, Georgina, and then I'll choose someone else for next week. Well, for 2 weeks from now. Go ahead, please.
It's okay. You can see.
Yes.
Okay. Good morning. Today I'm going to talk about ferroelectric to the ice under graphene confinement. It's an investigation. As general information, ferroelectric materials have an spontaneous electric polarization that can be reversed by the application of an external electric field. Can water show ferroelectric ordering? If water can show ferroelectric ordering has been a subject of debate among researchers because the small energy differences between ordered and disordered forms of ice. In this investigation, demonstrate that confining ice to a low-dimensional structure, in this case between two graphene layers, could influence the ordering of water and potentially allow for ferroelectric properties. It's important to say that when ice multilayer are present instead of a monolayer, the ferroelectric properties vanish. This indicates that the two-dimensional structure of the monolayer is important for its unique properties. The experiment. Upon nanoelectromechanical confinement between two graphene layers, water forms a 2D ice phase at room temperature that exhibits a strong and permanent dipole which depends on the previously applied field, representing clear evidence for ferroelectric ordering. Characterization of this permanent polarization with respect.
Sorry for interrupting. Are you presenting the other slides? Because I just see the first one.
Yes. Yes. I am presenting.
Yeah, okay, now I can see the other slides, yes.
Okay. Wait, well, continue. A characterization of this permanent polarization with respect to varying water partial pressure and temperature reveals the importance of forming a monolayer of 2D ice for ferroelectric. Well, the evidence. When ferroelectric ice is formed. In this investigation is demonstrate direct evidence for the formation of ferroelectric ice when water is actively confined to a monolayer between two layers of graphene. And you can ask why it is important. This advance enables the realization of project mechanical memory exhibiting 4-bit storage capabilities and no degradation after 10,000 switching cycles. The next question is why nanoelectromechanical is used? Because nanoelectromechanical actuation is employed to provide intimate and controllable contact between two graphene layers and to generate a polarization across their interface. You can see the result of the observation of the ferroelectric polarization. In the picture 2A, you can see the result of the Raman analysis. Raman is an electroscopy study. You can say that this analysis reveals a doubling of the p-type doping in the center of the suspended area and provides the first evidence for the ferroelectric nature of the process. In the picture 2B, to confirm the ferroelectric properties of the assembly, the researchers conduct electrical transport measurements which help identify permanent changes in the capacitance. This result indicates the formation of mechanical contact between the two graphene layers. In the picture 2C, researchers investigate the changes in tunneling electroresistance at different polarization conditions. And you can see that a non-linear curve confirms the presence of an injection barrier from longer polarization conditions and different times. In the picture 2E, you can see the last evidence for ferroelectric ordering that is obtained by high-frequency measurements. Variable frequency excitation reveals a monotonically changing dielectric constant. And in the picture 2F, it shows the change in polarization after the graphene is brought into contact. And this confirms the presence of ferroelectric ordering that is stable once generated. Thanks. You can follow me on my social sites for more information about materials.
Okay, thanks, Georgina. I didn't quite understand a couple of things. Well, first of all, why will ferroelectric ice will be useful?
electric applications for the formation of, like the realization of rocket.
Like what?
When it's like the mechanical memory with more capabilities.
Okay. How does it work? Like, it's ice, right? It can easily convert into water. How do you maintain it? Is it because of the graphene confinement? It will keep it stable for how long? How does it work?
For how long? I don't know. But it's a recently investigation. For how long I don't know. It's
So
like it's like
what's the graphene doing? Is it only keeping the ice alive, let's say, or is it doing something else? I didn't quite understand that part.
for now. It's only that demonstrate that to the eyes has ferroelectric ordering for now.
No, but what's the graphene doing?
The graphene permit that to the eyes is stable.
So it's only doing that. It's not
Yes.
really contributing to something else. It's only maintaining the 2D eyes alive, literally.
And permit the polarization.
It allows polarization. Okay. Um, where did you find this paper?
It was an investigation that I found in LinkedIn, and I investigate the paper and the, the paper and the time that I sí, sí, en LinkedIn, yes.
Can you go to slide 4, please? Okay. Can you explain again to me picture C and well, figure, I don't know what figure. Well, figure C and figure F.
Yeah, okay. In the picture to see is the change in different polarization conditions. And in this picture, the researchers identify a formation of an injection barrier. I forgot to say it, but they identify the formation of an injection barrier. And this change in injection barrier demonstrate the initially monotonic in polarization. But basically only demonstrate that the condition of polarization in different conditions and times.
Okay, yeah, but I don't really get it. So figure C, you're just comparing current and voltage, right?
Yes.
And I can see that, I guess, with increased time, you get a higher current with the same voltage. What were they measuring on? Like, for what? How? What was the relevance of that test that you're showing me in figure C? I don't get the importance of that. Like, for what? And I guess it is really because I'm not really understanding the end goal of the research. at least some pictures here do not really go I think with the end goal of what you describe.
Yes, I understood that only I only shout the different polarization conditions. I don't know how to know what to know.
But I don't really see a different polarization conditions, or are you talking about polarization conditions with you're just referring to different time? I don't really get it. But okay. Okay. Yeah, there's a lot of things that I'm not clear about this receipt, but it's okay. Um, remember to present things that you understand, okay? That you are able to explain. Um, Becky, I I remember you were selected last week. I did choose someone, and I think it was you.
Yes, I'm going to present now.
Okay, please go ahead. Thank you, Georgina.
It's okay.
Okay. Good morning.
Interesting. We're gonna talk about that towards the end of the class.
Good morning, teacher. Good morning, partners. I'm going to present about electrical steering. Mm, Well, uh, this is the problematic. At present, the automobile has become the main means of transportation for most of the humanity, but unfortunately, it is the worst leading pollution of the environment. The problem of ecological safety has now become of exclusive importance. The proportion of toxic substances that are released by motorized transport exceeded 60% of all emissions in industry. In addition to the fact that traditional or combustion motors don't take advantage of all energy, they generally have a maximum efficiency of 30%. Uh,
Sorry for interrupting, Becky. Can you speak louder, please? Because there is a background noise. I don't know if you're wearing your headphones or something, but there is a background noise, and I can't really hear you well. So if you can get either close to your microphone and speak louder, or just get rid of your headphones, that would be appreciated.
well, continue. Um, Before the motor was invented, vehicles were self-propelled by steam. A lot has changed our life since then. A lot has changed the motors in recent years, now offering less energy consumption and less pollution. In view of this problem, Tesla Motors launched a line of electric vehicles. Elon Musk, co-founder of the company, related that they sought to create a 100% electric and non-hybrid car. After so much research and tests, they came to the conclusion that the only motor capable of granting the demanding benefits that had been raised was the induction motor of Nikola Tesla. Say that they used the original plans of the patents and didn't change anything, only a small adaptation to work with the components of the 21st century. The result was a powerful car with great autonomy. Thanks to the efficiency of this motor, So they decide to call their company Tesla as a tribute to Nikola Tesla. But what type of motors are used in electrical vehicles? Fine. I'm going to talk about the permanent magnet synchronous motor. Currently, most electric vehicles use the synchronous permanent magnet electric motors. This is a device that transfers electrical energy into a mechanical energy through the action of magnetic fields generated in their coils. They are a rotating electric machine composed of a stator, and this is the stator, the external part, and the rotor is the moving part of the motor, and is inside of the stator. And the rotor can be wound with copper, aluminum, or permanent magnet, which is the most innovative technology. The stator is the external part, as I said, of the motor, and is wounded with copper too. This motor must be able to meet certain requirements. The requirements are the efficient in speed range in which the vehicle is most frequently driving, a high revolution to allow the vehicle to reach a high maximum speed, high torque to allow a quick start of the vehicle, and a powerful hill climb. It will be economical, compact, and lightweight. Rotor and stator materials. The properties of a motor also depend heavily on the electrical steel used as the core material. From an electric steel coil, hundreds of steel are obtained. This is the electric steel sheet. Then die cutting begins to remove the stator and rotor. Electric steel, also known as silicon steel, is an alloy of iron and silicon that is used to make the cores of electric motors. This type of softer steel can generate various magnetic properties, has high permeability and low amounts of core loss, and allow iron loss or energy loss too. The principal role of the electrical steel. Now I will try to explain why electrical steel are needed in an electric motor. The operation of an electric motor is based first of all of the copper windings, where will be put in of the pairs of windings, and this injection of current will lead this injection of current will lead to the magnetic field that will be able to generate a flux, and this flux will be able to deliver a torque in an electric machine, and therefore an output power. The goal of laying electric steel is that when you put steel inside of the copper of roll, more current will be generated than if nothing was put into it, and that is due to the fact that silicon steel is ferromagnetic. Such behavior is required in the magnetization graph that provides the amount of magnetizing current that is needed to achieve a certain level of induction. Will be proportional that is generate the torque. So the main function of electrical steel is to have a very good level of polarization or induction. This means that the little magnetization current is needed to achieve a higher flux than Earth space. Now, what is happening during this flux generation process? In fact, there is a magnetization process underway. The interior of the steel is changing in terms of magnetic structure, and this will lead to loss within the steel. That is why the motor heats up when it makes it work. It because inside the steel there are irreversible processes that generate heat that is not effective for the mechanical power output. So it is required to have electrical steel that have a good flux generation and do this with minimal loss. Uh, um, fine, finally, we have the selection criteria of electrical steel. The sample of the right is an example of four materials of industrial grade, 0.35 to 0.50. It is only to indicate that for a given level of loss, it is possible to make materials that have a different behavior in terms of magnetization curve. And this means that in case of that example of the four materials have higher magnetization. We can see at this part. Some materials have higher magnetization while others have lower. If you find yourself in the situation where, for example, I will say that for the torque I need to have in my motor, I want to be at 1.5 Tesla working point with the graph above, you will be in the situation where you will need less magnetization current. Then if you have to go the bottom graph, which is less permeable material. This means that the way the material is behaving in terms of magnetization will influence the amount of magnetizing current that is near, and therefore also the amount of copper that is near in the motor. So the use of material with better properties is this regard will not only have a good influence on the performance of the motor, but it can also reduce the cost of the engine because it can use less torque of winding in the costing. Copper is still quite a bit more expensive than steel. So that would be the first property that to discuss. And then the second property was the losses, the loss. Now, if it comes to reducing loss in steel, if on the middle graph, if you if you put more alloying elements, you will reduce the saturation polarization. So we're trying to make lower degrees of loss. You are reducing the saturation polarization, which is not a good point, and also because of the content of the alloy, it will have an influence of the material properties because the tensile strength will increase. And the last point, but not less important, is that when more alloying elements are placed in this graph, from the left to the right, the thermal conductivity will reduce. So summarizing everything to end, to reduce loss in something that needs to be observed very carefully. It is not simple putting more alloying elements because that has an impact on the saturation polarization, which is not positive. It can increase the resistance, which is good if you have a high-speed rotor. When materials with lower loss are created, it will have reduced the amount of heat that is generated in the steel, but the total amount of heat that is in the engine that comes from the copper loss and the iron loss still needs to be evacuated, and the thermal conductivity will have become more difficult. Finally, we have some disadvantage of electric motor and electric steel. Thanks.
Okay. What's the saturation polarization?
The saturation polarization is when the material cuando el material llega a su punto máximo de polarización ya no puede adquirir más magnetización. Es decir, que los materiales por lo general tienen un grado de magnetización. Entonces, la saturación es cuando el material ya no puede adquirir más grado de magnetización, así se le ponga un campo magnético.
There's a difference between magnetization saturation, saturation magnetization and saturation polarization. You were talking about saturation polarization, not saturation magnetization. What you just described is saturation magnetization.
Yes, I confused. Sorry. It's called magnetization of saturation of to the saturation, the maximum saturation that can a material have, a material ferromagnetic have. Usually it is characterized usualmente esto está caracterizada por la orientación paralela de todos los momentos magnéticos en el material. Se llama magnetización de saturación a la magnetización máxima que puede alcanzar un material ferromagnético.
Okay, not only ferromagnetics can attain magnetization saturation, and again, there's a difference between magnetization saturation and polarization saturation. Okay. Anyways, we're gonna talk about electrical steel today, so it's fine. Well, hopefully today, if not next 2 weeks from now. Thank you, Becky. Okay, let me choose someone for next week, and then, well, for 2 weeks. Melanie, have you presented? Melina's here. Melly. Does anyone remember if Melina has presented? No. Okay, so you are presenting in 2 weeks, Melly. Okay. Okay, great. That'll be it. Let's go to, where is it? Oh, here. Okay. Okay, let's continue. Okay. Now let's go with ferro and antiferro comparison, and again putting concepts of quantum mechanics there so we can understand why materials behave in certain way. So if you remember, iron, cobalt, nickel, all those metals have unfilled bands, right? And such as in copper, there is an overlap, and such as beryllium, sorry, there's an overlap between the D bands and the S bands, right? You can see from the graph, you can see there is an overlap of the bands. In these materials, and you might remember this, we have, or you have, a density of state that is relatively large. And that is because that D band can obviously accommodate up to 10 electrons and it's unfilled. Therefore, you have a large density of states. Now, let's, for example, look at nickel. Nickel has a density of states that is very large at the Fermi energy. So you can see here the graph, right, of density of states versus energy. And you can see for nickel, right, it is a very large value. So because you have a very large value of density of states, you only need a very small energy, a very small amount of energy to transfer a high number of electrons from one spin to the other. So from one direction of spins to the other, from one half to the other. Because you already have a large or significant density of states. Now, there is a difference obviously between paramagnetic and ferromagnetic materials, right? In paramagnetics, it is the magnetic field, the external magnetic field, so an external energy is needed to accomplish that flip, that spin alignment. You really need that extra energy coming from outside, coming from that external field, so that my spins can align. In ferromagnetic materials, this alignment is spontaneous. And it actually happens because these materials have very small magnetic domains, which are about 1 to 100 micrometers in diameter. So that's why it's very easy, and it's also spontaneous, because you really need a very small energy, because you already have a very large density of states. So you really need a very small energy, and that's why it's very easy, and electrons, sorry, spins can align spontaneously. Now, whenever we're talking about ferromagnetism, we should be able to explain where is that energy coming from. That energy that allows me transfer electrons into higher energy states. Well, that energy is called the exchange energy. It's an energy that is set free when we have equal or similar atomic systems, and we couple them, we join them together, right? So that they can exchange their energy, and therefore it becomes so easy for spins to align. So you can see here, for example, the Fermi energies for iron, cobalt, and nickel, right? Nickel having the largest. And look at copper, right? This is just a comparison between these four. Remember, copper, we said it's diamagnetic, and look why. Because its density of states at the Fermi energy is very low. Right? It's very small compared to nickel, to copper, to cobalt, to iron. You have very large density of states at their Fermi energy values. Okay, any questions there? No. Okay. So let's try to put an analogy here. I don't know if any of you have ever played a violin. Imagine you are playing violin, right? The strings, if you tune them, right, at almost equal pitch, you will have a vibrational pattern of those strings. They actually will vibrate in a parallel fashion. They will be oscillating in a parallel fashion. Those, just consider two strings, right, of the violin. And obviously, because they're vibrating, there will be a restoring force, a restoring force that takes them back to original position, and then again vibrate, and then again come back to the position, again vibrate, again come back to the position. So that restoring force should be really small, because it's really a small vibration, right? Just imagine literally two strings of a violin. Therefore, the frequency must be small. Well, that analogy actually demonstrates that two coupled and symmetrically vibrating systems will have a lower energy than individual systems vibrating by themselves. So we can apply that to ferromagnetism. Obviously, it's more involved. You just do not have only two strings, right? You have many atoms, right, vibrating. But the thing here is they are vibrating symmetrically, and they're coupled. So we have coupled systems. And so if you want to get into the math of that, the math of that explanation is quite involved. You need a special Schrodinger equation. And so we're not gonna get into that. The thing here is, or the important thing here now to remember is, those restoring forces, right, that happen or that occur in order to maintain my atoms in position, or at least take my atoms back to position, are related to potential energy. And this potential, or that potential energy, depends on the exchange forces between the nuclei. So imagine an atom, right? Two atoms. You have nuclei I and nuclei B. You have electron 1 and electron 2. So there will be a force between electrons. There will be a force or an exchange force between the nuclei. And obviously, those interactions between the nuclei and the neighboring electrons is what allows me to get that exchange energy. Well, that allows me to get this exchange integral that at the end, as I said, is related to the exchange energy that I just talked here. And so this obviously is related to this the relationships between electrons or nuclei and neighboring electrons around the nuclei, right? So, for example, the distance between the radius from nuclei sorry, to nuclei B, the distance from nuclei to electron 2, the distance from nuclei B to electron 1, and the distance from electron 1 to electron 2. So this is called the exchange integral, and you can see, sorry, the exchange forces are obviously gonna decrease with distance, right? So the larger the distance between, let's say, electrons, or the larger the distance between nuclei and electron, it kind of makes sense that the force is going to decrease, right? And you can see that from here, obviously. If any of these becomes larger, right? And especially just if this becomes larger, or if this becomes larger, obviously this is gonna decrease, right? And it makes sense. So if you want to really understand what this, because you see here positive and negative values, right? If you have an exchange integral that is positive, that means that parallel spins are energetically more favorable than anti-parallel spins. Why? Because you can see it will be positive if either this is small, so the distance between electrons is small, it can also become positive if there is a large distance between the nuclei and the neighboring electrons. So if this is large, or if this is large, these terms are gonna be small, right? And if they're small, because they're negative, this term is gonna be large, right? And so that will give me a positive exchange integral. If I have either a small distance again between the electrons, so that will be equivalent to having a small radius of orbit, right? So that means electrons are close to each other. Or if I have a very large distance between the nuclei, or from my nuclei to the neighboring atom, right? That will lead me to a positive exchange integral. So you can see here actually the graph of that exchange integral versus the ratio of the interatomic, the nuclei distance, so the distance between two atoms. And RD is just equivalent to R1, 2. So RD is the same as that. So the radius of between electrons is the same as the radius of electron orbit, RD. Okay. So you can see from this curve easily the separation between ferromagnetics and antiferromagnetics. If the exchange integral is negative, the materials are antiferromagnetics. If the exchange integral is positive, the materials are ferromagnetics. So you can see manganese and chromium are not ferromagnetics. And this actually, you can see manganese is quite close to, it doesn't really have a large negative value, right? It's kind of close to at least become zero or positive or have a positive value. And actually, if you, for example, dope or alloy your manganese with nitrogen, this interatomic distance will be increased, right? And if this increases, obviously, manganese with alloyed with nitrogen will be somewhere here, so it will become ferromagnetic, for example. So that is how also you can play with your materials and say, oh, so I can do this and I can change the behavior of my material. You can also see here that cobalt should have the highest, whereas nickel and the rare metals should have the lowest Curie temperature. And that is actually true, just because of the exchange integral. The largest value found in copper, the lowest values found in the rare earth metals. So this one should have the highest Curie temperature and this one should have the lowest Curie temperature, and that is actually true. So you can see with quantum theory why some ferromagnetic properties couldn't be, or can explain some ferromagnetic properties that couldn't be explained with the classical electromagnetic theory. Okay. Any questions, guys? So now let's go to the number of Bohr magnetons in ferromagnetic metals. So the number of magnetic moments, which is the same, right? Let's consider nickel again. Remember, nickel has the band overlapping, right? We saw that there is an overlap between the 3d and the 4s bands. Because of that band overlapping, those electrons in the combined 3d plus 4s state, they will occupy first the lower S band and fill up to pretty much all, or will pretty much fully complete the 3D band. It doesn't completely fill it, but it kind of gets to a value almost full. And that's why actually, experimentally, it's been determined that the 3D band in nickel is filled by 9.4 electrons. So if we need to estimate the number of Bohr magnetons, we need to apply Hund's rule. Remember, Hund's rule tells me that the electrons in a solid fill the electron states in a manner such that we can maximize the imbalance of spin moments. And remember, so Hund's rule is just the simple, right? Remember, if I have, let's say, D can fill up to 10 electrons, right? So you fill the first 5, and then you go 6, 7, 8, 9, well, 9.4, right? In this case. So basically, if you have filled 9.4 electrons in the 3D band, that means you have 5 spins down, 5 spins up, and an average of 4.4 spins down. Therefore, there is this imbalance, right? This imbalance, which will be 0.6 spins moments. Well, so that is the 0.6 Bohr magnetons per atom that nickel has, and that you can calculate. And you can see here, it was found experimentally. You can do the same for iron, for copper, for gold, for gallium, for other metals. Okay, so you can calculate that well, or obviously you can also calculate the experiment. Any questions, guys? Okay, let's go here. Now, let's try to understand how nickel-based alloys behave. And actually, let's look at nickel copper, for example. If you look at the electronic configurations, copper will have one more valence electrons than nickel, right? So let's alloy copper. So let's put copper into nickel. Well, that extra electron from copper will progressively fill the D band. That, remember, nickel, we said, right? Nickel doesn't really have a filled D band, right? It has like that empty space of an average 0.6 electrons. So if I put copper, well, that extra electron will start saturating or filling the D band. So it will compensate for those unsaturated spins of nickel. Therefore, the magnetic moment per atom of that copper nickel copper alloy will be reduced, right? Because I now will be able to basically compensate all those unsaturated spins. That's why also the Curie temperature will be reduced. So nickel, again, lacks an average of 0.6 electrons per atom, right? In order to complete the spin saturation. That's why you need about 60% of copper atoms in order to completely make nickel reach a zero value of magnetic moment. And that's what you see here. So look at copper. This is for nickel, right? This is for nickel. Magnetic moment, or Bohr magnetons, which is equivalent, reaches a value of 0 once copper reaches 60%. But you can definitely see that if I don't have 60 atomic percent, let's say I have 50 compared to 20, you can see that the number or the Bohr magnetons is decreasing, and obviously the Curie temperature is also decreasing. Look at zinc. Zinc has 2 extra electrons, right? So you have more electrons, it will saturate more easily, and that's why you only need around 30% zinc in order to make nickel reach a zero value of Bohr magnetons. Now, if you look at palladium, for example, palladium has the same number of valence electrons as nickel. Therefore, it doesn't change its magnetic moment, right? And it doesn't change its Curie temperature. Okay? Any questions, guys? Okay? So, if you look at the graph, right? What will happen with a nickel copper alloy that has a concentration greater than 60%? Well, they will be no longer ferromagnetic, right? You will expect them to be diamagnetic. And they are actually, well, then it becomes a theory. In reality, they are paramagnetic. But the thing is, and it makes sense, they are no longer ferromagnetics because you don't have any Bohr magnetons left. What other materials are ferromagnetics? Well, rare earth elements, because they have unfilled F shells, like nickel that has unfilled D shells, right? Okay, guys, I think that will be it for today. I'll see you on Wednesday. Remember, you have your quiz on Wednesday. You have also your problem set due. So just to remind you that. That'll be it, guys. Thank you for coming. And I'll see you on Wednesday. Take care. Any questions you can ask.